we have done up to this, and quickly I will go to the few slides. So yeah, this is the definition of B. B is the change in pore pressure due to units change in cell pressure, and A bar is change in pore pressure due to units change in deviator stress or principal stress difference. Then if I consider some special cases, for example, if I take fluid is really incompressible, so Cw is equal to 0, and when you put Cw is equal to 0 here, so this quantity becomes 0. This is the compressibility of water and or fluid, and this is the compressibility of soil grain skeleton. So this quantity becomes 0, so 0 plus 1 is 1, so B will be almost equal to 1. And equation for the change in pore pressure will be delta sigma 3 because B is 1 and A into B, that is A into this. And if it is a dry soil, means pore fluid is now air. So in that case, the compressibility is very large here. So so in that case, so this value is quite large, and when you put 1 upon quite large value, so B value will be very, very small, and delta U will be tending towards 0. So there will be no development of pore water pressure in case it is air. For partially saturated soils, the equation will be same, and as the degree of saturation varies from 0 to 1, the parameter B will vary from 0 to 1. And this is the kind of the variation. As degree of saturation varies, parameter B will be varying, and it will be almost equal to 1 for completely saturated case. You don't have to go in much detail. You just should have some uh, uh, feel of these things. And to determine these parameters, we have to do the undrained test. And procedure is simple, that you increase the cell pressure, and pore water pressure measurement is possible. So from there you get this, and then you can get parameter B. Similarly, under undrained condition, increase the deviator stress and find out what is the increase in pore water pressure, and also what is the increase in deviator stress, and then you can calculate A bar. And for fully saturated soil, yeah, you can also conduct consolidated undrained test. So B equal to 1 for soil which are fully saturated. So basically you have to remember this equation and this procedure to get the value of these parameters. Now parameter A may be negative also. So here A is the change in how much change is occurring in pore water pressure due to change in deviator stress. So it depends on whether the soil is dilatative type of nature or it is contractive in nature. So depending on that, if it is trying to dilate and it is undrained condition, so it will try to suck water, and it tries to suck water. Water is not coming because it is undrained condition, so you are going to have negative. So this A value may be negative as well as positive. These are some typical values. We don't expect you to remember or mug up these values, just to have the idea. At the time of failure, it's very important for us to analyze the things. So for very loose, fine saturated sand, A is very large because they are going to compress. So pore water pressure is going to increase. And if it is extra sensitive quicksand, then it is 1.2 to 2.5. Normally consolidated, it is 0.7 to 1.3. I'm not expecting you to remember, but if it is pre-consolidated, very heavily pre-consolidated, then it goes to negative range. So if you look at this diagram here, so as the over consolidation ratio is increasing, value of A goes on decreasing, so it can become negative also. So over consolidated clays, it becomes negatives. So this is, I think, all about what I wanted to say about the this pore pressure parameters. Now I will discuss some few general things about the shear strength behavior of how saturated clays and how sands are going to behave. I'm not going to discuss any new thing, just the principles which we have already discussed, that I'm going to just refresh once again. So if it is a cohesive soil, means if it is clay and you are doing undrained test, so you know in undrained test, sigma 3 dash is not going to change. So sigma 3 dash remains the same. And every soil will be having some C dash, phi dash also. C dash may be 0. So in fact, the effective stress envelope will be something like this. So this is effective stress envelope. Effective stress envelope. And this is sigma 1 dash. Now, when you are doing any test on in this condition, then when you apply cell pressure, so let us say you apply this much cell pressure, sigma 3, then what is going to happen is the pore water pressure is going to increase. And when you shear it, it is going to have the same, because the effective stress circle diameter is this much. So under undrained condition, this second one, sorry, it is just a minute. So this is sigma 3. So what is going to happen is when you apply cell pressure or deviatoric, when you apply deviatoric stress, so pore water pressure will develop. So same pore water pressure is developing here and here. So you will have this sigma 3 and sigma 1 value. You are doing some another test, so this will be sigma 3 and sigma 1 value. But because sigma 3 dash is same, so sigma 3 dash is same, and you know sigma 1 f dash is a function of sigma 3 dash and c dash and phi dash. So this remains the same. So sigma 1 minus sigma 3, and you know equal to sigma 1 dash minus sigma 3 dash. So what you have to remember is that all the circles for total stress will have same diameter, and you are going to get phi u is equal to 0. So phi undrained is 0, and this is the C undrained value. And that will be equal to shear strength. Tau is equal to C plus sigma and phi. This I had discussed earlier also. So phi is equal to 0, tau will be equal to Cu. Now, suppose we do consolidated undrained test on this clay sample. So I have taken two cases, case 1 and case 2. In case 1, we have applied a consolidation pressure 10 kPa, and it is consolidated, means now sigma 3 dash becomes 10 kPa. Now in stage 2, what we do is yeah, so stage 2, the cell pressure is 10 kPa only. So this is the, when you shear it, this is the, let us say, the Mohr circle. Now I do another test where consolidation pressure is 10 kPa. So we have applied 10 kPa of the consolidation pressure. Sigma 3 dash is again 10. Here also sigma 3 dash was 10. But now in stage 2, what you have done is you have increased the cell pressure and you have gone up to here. So this is sigma 3 value, but sigma 3 dash was same, so the diameter will remain same, so you will be getting this. So this is the Cu value. This is what we discussed in the previous slide. Now suppose I do another test and I initially apply consolidation pressure of 25 kPa. So what happens now? Sigma 3 dash will be equal to 25 kPa. And as you know, sigma 1 dash is a function of sigma 3 dash and C dash and phi dash. So now it will be more than what it was there in previous case. So and stage 2, what we have done is we have increased the cell pressure to 30 kPa. So 30 kPa is this, and you will have a Mohr circle at the time of failure equal to this. I wanted to emphasize here that this particular diameter, this diameter or this diameter, it is a function of sigma 3 dash. That is important thing for you to remember. So in first case, sigma 3 dash was 10. And now in second case, we are doing the test repeatedly. We are doing the test. Consolidation pressure, we are keeping 25 only. And cell pressure, we are varying. We can have 30, we can have 40, we can have even 0. You can have 0 here. So in case of 0, you are going to get this circle. So you are going to get this circle and pore water pressure will be negative. It will be unconfined test. So what we learn from this is that as you do the consolidated undrained test under different cell pressures, consolidation pressure, sorry, the Cu value will keep on increasing. So you will find that Cu increases. And we have plotted it here. So effective consolidation pressure, effective means which has been transferred to the soil, and Cu varies like this. So it passes through 0, but there is one thing which you have to remember. This is going to happen as long as the soil is being loaded first time. Loaded first time to this load. If it is already pre-consolidated, if it is normally consolidated, then it is going to happen. Then this line will pass through 0. So you are going to have 0 apparent cohesion here. But if it is pre-consolidated, then in the pre-consolidation range, the behavior will be little bit different. So it will be a curvilinear kind of the behavior, and you will be having this kind of the relationship. So that you have to remember that if it is below pre-consolidation pressure or above pre-consolidation pressure, behavior will be different. We will try to see this thing again here if I draw the stress, the envelopes, failure envelope. If it is, if I am doing a consolidated undrained test, so we are consolidating it at certain pressure. An effective failure envelope or total failure envelope for both we can plot. So if we plot the effective stress envelope, it is like this. So this is one circle, this is another circle. You are going to get effective stress envelope like this. So this is the case when it is normally consolidated. And if you plot the total stress envelope, this is also going to be 0. It will have the intercept 0. So you have to remember it that normally consolidated soil or soil, whether it is effective or it is total. So for clays, you are going to get C is equal to 0. So they pass through here. So they pass through here. But this is going to happen only when it is normally consolidated. If it is over consolidated, then this diagram shows you the picture. So this is the range the where the pressure range was. This is the pre-consolidation pressure. So if you do the test in this range, means the soil has already been subjected to a pressure. You can try to remember it, making an analogy. Suppose you are compressing a soil and then you are removing that load, then it is going to develop some cohesion. The particles will be sticking to each other. But if you are first time loading it, then the cohesion will not be there. So effective stress envelope and total stress envelope, you should remember that they are going to pass through the origin. So C will be 0 in this case also, in this case also. But if you are working in the range where the confining pressure is less than the pre-consolidation pressure, then you are going to get C as well as phi both. So you remember it this way, that C and phi both will be available if it is pre-consolidated. Otherwise, it will not be having C and phi under consolidated undrained test. If you are doing the consolidated drain test, then there is no question of total stress because we are not going to get it. Total stress and effective stress, they are same. There is no pore water pressure development here. So it remains, the basic fundamentals remains the same. So for normally consolidated soil, you are going to get C dash is equal to 0. For over consolidated soil, you are going to get C dash more than 0. So, and here in this case, you get only the effective stress envelope. You don't get total stress envelope as we were getting in CU test. These diagrams show you some behavior of stress strain and volume change in case of the fully saturated clay soils. So if you are doing a test on over consolidated soil, then it is very well, you can say it's hard soil, it will be stiff soil. I can use this term stiff soil, pre-consolidated. So if you plot the displacement or the strain, horizontal displacement in case you are doing some shear test, or axial strain if you are doing the triaxial test, then the behavior will be something like this, that shear stress goes up and there is a well-defined peak. Well-defined peak, it is just like a brittle behavior, sudden behavior, because the material is strong, stiff. Material is stiff, I should call it stiff. And after the failure, then the stress goes down. And if you keep on shearing it, then it approaches a value which we are going to call as residual. Residual means after failure, the strength does not become 0. There is some strength remains, which remains there. So it is going to be there. And if you have a normally consolidated soil, it is being loaded first time to this load, so to this stress. So the stress will be gradually increasing, and in fact you don't have a very well defined failure point here. You have to use some arbitrary value of the strain which we take from the experience. So let us say if I take around 10% or 15% of axial strain, corresponding to that point, I can assume that failure has occurred. Otherwise, if you keep on shearing it, then it is also going to join this residual strength asymptotically. So what happens? Normally consolidated and over consolidated, both soils, when they are sheared to large displacement, then their residual strength will be almost same. So here I have shown it here. So peak is here and then residual is here. So they go up to residual. Now the second diagram is the same diagram which tells you what happens under if you are doing the analysis testing in over consolidated range. Then you have an intercept with the y-axis here. If you are testing normally consolidated soil, then it is not going to have y-axis. This is already I have discussed. So for loose sand also it happens like this, that there is gradual increase in the stress, and in case of dense sand or over consolidated clay, there is well defined peak. Yeah, volume change. Here it is volume change. If it is dense sand, please remember, if it is dense sand or pre-consolidated clay, then overall behavior is that volume is going to increase finally. Though initially when you apply the load, there will be some decrease, but finally it is going to be increasing load. So the volume is going to be expanding. So we call it dilation. And if it is a loose kind of the soil or it is normally consolidated clay, then it is going to get compressed. So its volume will keep on decreasing. So, and the reason is it is the arrangement of the particles. If the particles are very well packed, very good arrangement is there, and when you shear it, this best arrangement gets disturbed. This arrangement was attained by the soil in millions of years. Now you have disturbed it, so they get displaced. Particles are not going to crush, so they are going to expand. The soil is going to expand in volume. Remember, if it is loose, then it's going to expand. If it is dense, it is going to, sorry, if it is loose, then it is going to compress. If it is dense, then it is going to expand. So this is let me go to the last part, and now same thing, almost similar things are going to happen with saturated sands also. So if you do a drain test on a saturated sandy specimen, now we take sand, and in case of sand also, let us say we take two types of the sandy soil. For example, we took pre-consolidated and normally consolidated. So here one soil is having very high initial void ratio, so it is loose. So void ratio is high, that means it is loose soil. And another soil is same type of the soil, but the void ratio is very low, that means it is dense soil. So we apply cell pressure, then stage 2 we apply deviator stress, and cell pressure is maintained at a constant value. So what happens in case of dense sand? Same thing happens. So here if you plot axial stress and axial stress versus strain curve, then for dense sand you are going to get a very steep curve and clearly defined peak, and after that there is a sudden failure, and then also again it reaches almost a constant value, which we are going to call as ultimate stress. So finally this dense sand is going to have this much stress, and this is the strength. If you are testing loose sand, so what happens inside that we'll discuss later on. Okay, so deviator stress in this case of loose sand, so it is loose sand here, and it is going to behave in the same manner as normally consolidated clay was behaving. So it is gradually compressing, and you may not have a very well defined failure. You have to decide where the failure has occurred, and it is going to approach the ultimate stress. Same thing as we had in case of clays. And if you look at the volume change again, so dense sand, as I told you, in case of clay also, and here also initially there will be small decrease in volume, otherwise it increases. So the volume increases. So here it is, volume is increasing. And the term which we use is dilation. This is a technical term. And if it is loose sand, then there is decrease in volume, and this term is called as contraction. So loose soil, it is going to decrease in volume. Now here, in case of sands, there is one additional thing which we are going to do. We are going to discuss it in terms of void ratio. If you take the dense sand, then what happens to void ratio? Because it is increasing in volume, so void ratio is increasing. In case of dense sand, the void ratio increases. In case of loose sand, the void ratio is high, so it is high void ratio, and then it decreases. It decreases. In case of dense sand, initially void ratio was small, void ratio was very small, and then it increases. So we have shown it here that during this shearing process, if it is dense sand, initially void ratio is low, and ultimately, though initially in the beginning there will be some decrease, but finally it is going to increase. The void ratio increases and it reaches a constant value. If it is a loose soil, then initially the void ratio is high, but as you go on shearing it, the volume decreases and void ratio decreases. So this value, it is very important value here. This is called as critical void ratio. So you should also know this concept that critical void ratio is the void ratio. If you test a sample, what it indicates that if you test a sample which is having this void ratio, critical void ratio, then it is not going to change in volume. So when the shearing occurs, please remember, when the shearing occurs, समाधि जी क्लास में हूँ मैं जरा अभी. So we have to remember that when you are applying deviator stress, when the shearing is occurring, then soil is either increasing in volume or decreasing in volume. So it has to happen. The third case is it does not increase, or either it does not, it is neither increasing nor decreasing, means volume is constant. So this is that case. So it is a special case. So corresponding to this void ratio, there will be no volume change. Otherwise, if it is dense, then it is going to become loose. If it is loose, it is going to become little bit dense. So this is critical void ratio. This concept should also be known to you. But here one more very important point is that this critical void ratio will be dependent on confining pressure. What confining pressure you are using. So what we do is to get this critical void ratio, suppose we are taking sigma 3 is equal to, let us say, 30 kPa. So we can do large number of tests. We take E is equal to small, initially a sample with smaller void ratio, then let it larger, then some larger value, then some larger value, then some larger value, and then you can find out what is that void ratio at which there is no change in volume. Initially, there will be increase in volume because you have taken E as small. E is small, so it is dense soil. Then finally you are taking loose soil, it is going to contract. Somewhere in between you are going to have critical void ratio, but it will be a sigma 3 specific, means for every sigma 3 it is going to change. Because when you apply 30 kPa of confining pressure, the soil itself is going to consolidate, its E value is going to change. So this critical void ratio will be different for different confining pressures. So this much you must remember. So here we have discussed that the dense sand, how it is going to behave, loose sand, how it is going to behave, and if it is at a critical void ratio, the volume change will not be there. And last diagram here I have shown here on x-axis if you take confining pressure, and on y-axis if you take critical void ratio, then as you go on increasing confining pressure, the critical void ratio will go on decreasing. If you are doing a consolidated undrained test, so now the situation will be different. Here we were doing earlier, we were doing the CD test. So CD test means drainage was always allowed. There was no development of pore water pressure. Now this is a very important thing here. Now you have consolidated the soil, and when you consolidate the soil, so sigma 3 gets transferred into sigma 3 dash. And now you go to the stage number 2, the shearing stage. And as I told you, the soil is either going to contract or it is going to dilate, unless it is in critical, having a critical void ratio. So if soil tries to dilate, let us say it is trying to dilate, it is trying to expand in volume. So it is quite dense soil. So what is going to happen? It is trying to dilate, but in the second stage, we are not allowing any water to go out or go in. So it is undrained condition. So when it is undrained condition, there is negative pore pressure is going to develop because it is trying to suck water. It is trying to expand, and the soil is trying to suck water. So there will be negative pore water pressure. And when there is negative pore water pressure, the effective stress, effective stress is total stress minus U. And if this U value is negative, then effective stress will increase. And if effective stress increases, and then what happens to strength? Strength is going to increase. So that is going to happen. So if the undrained condition is there and negative pore water pressure is developing, then effective stress will increase and the strength will increase. Conversely, if the soil is trying to, let us say, contract, it is trying to reduce in volume, and it will try to squeeze out water, but water is not allowed to be squeezed out. So water will be having pore water pressure. So there will be positive pore water pressure. Once there is a positive pore water pressure, so effective stress will be sigma minus U. So here U value is positive, so effective stress will be reduced. So strength will be reduced. Strength, I have been telling you a number of times that strength is a function of sigma 3 dash. Strength, we are talking what is the strength that can be derived from grain to grain contact, frictional and cohesive forces. Okay, so this is and if you are doing consolidated drain tests, let me explain one more thing here. And here also, if you are working in the range where void ratio is less than critical, or if void ratio is more than critical, then there will be different behavior. If you have done a CD consolidated drain test, then C dash will be 0. So this is the failure envelope. So C dash will be 0 for sand, and phi dash will be having some value. And this is the case of loose sand, and in second figure, this is the case of dense sand. So phi dash here will be phi dash dense, and phi dash loose. You can find it out by conducting the CD tests. and this value 5 for dense, it will be more than 5 for loose. That is one thing. Now we come back to drained if we are doing undrained tests. So if we are doing undrained tests, so try to see what happens here. So if the specimen is consolidated under same cell pressure and then undrained test is conducted. Now we are doing the undrained test. So what is the change here? That tendency of volume change will be governed by critical void ratio. So if you are in this range, where E is less than critical void ratio, there is going to be dilation. And when there is going to be dilation, we have already seen that due to dilation, there will be negative pore pressure and strength will increase. So here you can see this undrained strength will be more than drained strength. Whereas if you are working in this range of confining pressure, so here it is the void ratio is more than critical void ratio. So soil is going to, so here it is loose soil. So when it is loose soil initially, so when it is drained, when it is sheared, it is going to contract. Because of contraction, it is going to develop positive pore water pressure. Because of positive pore water pressure, its effective stress will reduce. And when effective stress reduces, strength will reduce. So it is going to have this much strength. So you are going to have this kind of the behavior in case of undrained soil. Similarly, you can also explain this diagram if it is a dense sand. So here again same phenomena is going to occur. So in this range the dilation is going to occur. So the undrained strength will be higher. Here undrained strength will be lower. The point which I wanted to emphasize here is that this is a complicated process, little bit more complicated, because the tendency of change in volume will be governed by the critical void ratio. So if you are testing a soil which is having more than critical void ratio or which is at less than critical void ratio, it is going to behave in a different manner. But the undrained and drained results will be differing like this. One important aspect of this is what is called as liquefaction. So what happens is when you have a loose saturated sand, so there is a loose sand. It can happen in sand, it can happen in silts also. So when there is a sudden shock, for example, there is earthquake or there is machine vibration, then what is going to happen? It tries to compress, and load is so sudden that undrained condition develops. So there is pore water pressure. So pore water pressure will be positive. That means effective stress reduces, or it may even become zero. Or when it reduces, the strength reduces, or strength even may become zero. And then when strength becomes zero, there is a failure. So this phenomena is called as liquefaction, and I think I have already discussed this phenomena. So this is what I wanted to discuss about the sands and clays. They have almost similar things, only some terminologies are different. And finally, I now come to a very small uh, chapter, very small topic, and that is stress paths. So I have discussed initially that suppose we take a soil specimen and we are testing it, and we have applied sigma 3 from all the sides. Let us say we are doing drained test. And in drained condition, I can do the analysis in terms of effective stresses here, or you can also discuss in terms of total stress. So when all round stresses were sigma 3 dash, so sigma 3 and sigma 1 were equal, so this was the Mohr circle. When you start applying the deviatoric stress, then you have one circle like this, another circle like this, another circle like this. So as you go on increasing, so let us say this is the failure envelope, and you can keep loading it till the circle touches the failure envelope, and then all these Mohr circles, they are explaining the stress state during path of loading. So during the process of loading, the specimen has undergone these stress states, and those stress states are defined by this circle. So people have found it convenient that rather than taking circles and drawing circles and it becomes cumbersome. So what they have taken, what they did was they took this point. So this point. So let us say this is the circle and I take this point. And rather than plotting this entire circle, I plot only this point. And this point, if I concentrate, it gives me all the information related to this circle. This point is having its center at sigma 1 plus sigma 3 divided by 2, and also its radius will be equal to sigma 1 minus sigma 3 divided by 2. So I know, if I know the x coordinate and y coordinate of this point, I get all the information about that circle. So rather than drawing the circles, these stress points are plotted. They are not failure points. Please note. So it starts from here, here, here. Even at this particular last circle, it is not a failure plane. Failure plane is somewhere here. So failure plane is given by this point. Okay. So this joining. So when we join these points with a smooth curve, then what we get, there is a relationship, how stresses have been changing, that we can find out. And this particular curve is called as stress path. So this tells you how the stresses have been changing during process of loading a specimen. And we did it when we were calculating the shear strength parameters. This sigma 1 plus sigma 3 by 2 is denoted by letter P. So if you are using P dash, that means it is effective stresses. If you are using Q dash, then it is, if you are using P, then it is total stresses. So this curve or straight line connecting the relevant stress points is called as stress path. And it gives the clear representation of the successive states of stresses which the specimen has undergone. Here we are talking about the lab test, but same thing can happen in the field. In the field, suppose this is the soil sample and you apply some load here. So it has been consolidated and then now load has been applied. So you can draw this stress path, how it has traversed. And you can draw it in terms of effective stresses, or you can also draw in terms of the total stresses. So this is nothing but we already discussed it. P and Q, we have plotted it, and from there we in fact obtained the shear strength parameters. So we did it something like this, that we derived this equation. This was the Mohr envelope failure envelope, which touches the Mohr circles, and then we converted into this straight line equation. So sigma 1 minus sigma 3 by 2, we are putting Q. sigma 1 plus sigma 3, we are putting P. And here you can take any angle. There normally it is called psi. So this is psi angle. So here in this plot, in the second plot, we have plotted only these points. One point is here, another point is here, and third point is, sorry, third point is here. Please note that we are plotting now the final stress path. You see, the stress path for the third test was something like this. So this is the stress path for the third circle, and this is the stress path for the second circle. This is this path for the first circle. And can you get this angle? If it is a CD test, consolidated drained test, means sigma 3 dash always remains constant and sigma 1 dash keeps on increasing, then mathematically it's very simple. Every time you are joining the top point of the circle. So y-axis, y coordinate is radius, and this is also radius. And when you go to this point, then this height is radius equal to radius. This is also radius. So this angle is going to be 45 degree. So these are stress paths of different circles. But if we join only these points, only these final points of the failure circles, so this is what we have done here. So this particular line is called as KF line. So what happens is if you start, if you know this KF line, and there is some stress path which is moving like this, then when this stress path touches this KF line, the failure will occur. For failure to occur, the stress point should lie on KF line. I am taking some examples here. So let us take one example. If sigma 3 is kept constant and sigma 1 is increased till failure, so sigma 3 is kept constant here, so sigma 1 is being increased. This is the usual case which very commonly we have been discussing. So, and then you can join them, and I have already discussed this angle will be 45 degree. Another example I have taken is if sigma 3 and sigma 1 are increased or decreased by same amount. Now let us see what happens. So P is equal to sigma 1 plus sigma 3 by 2, sorry. And Q is equal to sigma 1 minus sigma 3 by 2. Now suppose what I do is I do a test and I am increasing sigma 1 and sigma 3 by the same amount. So delta sigma 1 is equal to delta sigma 3 is equal to, let us say, some value 10. So what is going to happen in this case? Q is not going to change because sigma 1 is also increased, sigma 3 is also going to increase. So if I start from this point, so next point is P is going to increase, so P will be here. So if I increase it further 20, so you will get another point, third point, fourth point, fifth point. So stress path is going to move like this. If I am decreasing, what is going to happen? So if I am decreasing them, so sigma 1 is decreased, sigma 3 is decreased. So yeah, when you decrease, then the circles are going to go like this, and these points, stress path will be moving in this direction. So if stress path is moving in this direction, you should be able to tell me, if I say the stress path is moving in this direction, you should be able to tell me what is the relationship between delta sigma 1 and delta sigma 3. So it's easy. Let us take another example. Sigma 3 is decreased and sigma 1 is increased by the same amount. So let me draw the circle first. So this is one circle. And then what I have done is sigma 1 I have increased and sigma 3 I have decreased, and this amount is same. In other words, I am not changing the circle, the center. So center remains the same. So this is the third circle, fourth circle, and stress path will be this. So in fact, if I give you that there is a stress path which is making, let us say, theta degree angle, and you have to tell me what is happening with the stress changes, then you should be able to tell me how delta sigma 1 and delta sigma 3 are changing. So this is the way we can draw this stress path. Now for undrained test, you see sigma 3, we have kept cell pressure, we have applied some cell pressure, sigma 3, and now we are shearing it and it is undrained. We are not allowing water to go out, so U is increasing. So when U increases, sigma 3 dash will be equal to sigma 3 minus U. Cell pressure is being kept constant. So the total stress path will be moving in this direction. But as far as the effective stress path is concerned, as you increase the shearing deviator stress, pore water pressure will be becoming higher and higher, and effective stress path will be moving in this direction. And as soon as it touches the KF line, the failure occurs. So this is the concept which you have to remember. I will just solve one problem, and I think I have given this problem in the tutorial sheet also, so that will be the last thing. We have done a triaxial test and it was consolidated fully. The specimen was consolidated under an all-round stress of sigma 3. So we have applied sigma 3 dash equal to 200. It is consolidated. Now what we do was that under undrained condition, all-round pressure is increased to 350. So now we close the drains and now sigma 3 is increased to 350. And because it is undrained, so sigma 3 dash is not. Yeah, let us see further the question. So sigma 3 is 350 now. Let us see what happens. The pore water pressure then being measured at 144. So here at this place, when you increased the cell pressure, pore water pressure has become 144. So what is the effective stress? So sigma 3 dash is equal to how much? 350. And out of that, I subtract 144. So 602. Sorry, 306. Now he says this is the pore water pressure. So at the beginning of the stage 2, the pore water pressure is 144. Now axial load is then applied under undrained condition. Now we are applying load under undrained condition until failure takes place. Following results were obtained. Determine the value of pore water pressure coefficient B and plot the variation of what I wanted to do is I wanted to draw the rest of the things you can do. Draw the stress path. So I want to draw the stress path. So let us see how we do it. So principal stress difference is given to you here. They have given 0, 201, 252, 275, 288, 283. And pore water pressure is also given to you. So it is 144, 244, 240, 222, 212, and 209. And we are keeping sigma 3 cell pressure is 350. So cell pressure is 350. It is undrained. So we can calculate what is the sigma 1 value. Sigma 3 minus sigma 1 will be equal to this. So you can add this and sigma 1 minus sigma 3 plus sigma 3. So from there, so this is 350 plus 201. So you get sigma 1 equal to this much. 350 plus 252 So you get sigma 1 is equal to this much. So you get all the sigma 1 values. So you have sigma 1 values, sigma 3 values. So you can get P and Q. So sigma P is equal to sigma 1 plus sigma 3 by 2. So these values are available. Then you can calculate Q, and then you can draw this total stress, the stress path for the total stress. For effective stress, the P dash will change. Q will remain same because sigma 1 minus sigma 3 dash by 2 and sigma 1 minus sigma 3 by 2, they are equal. So you have to calculate the sigma 1 dash and sigma 3 dash values. So you have the pore water pressure. So sigma 1 minus U, that is sigma 1 dash, sigma 3 minus U, that is sigma 3 dash, and I have made one column here which calculates this effective stresses. So the effective stress path goes like this. So this is the way you can plot the effective stress path and total stress path. And you should be able to give me the answer if I give you the conditions that the effective stress path is moving in this direction, in this direction, in this direction, or in this direction, what is happening. So what's the time? I have taken 3-4 minutes extra. Let me stop here. So there is no time for discussion today. You can always have your questions. You can discuss with me on phone, or you can give me an email. If there is any topic, anything where you need special attention, please let us know. And so this is the last lecture. All the best for your exams, though they are very late. So, and I hope you will do good, though the online teaching is not that effective, but we have tried our best, and any help which I could be, for which I could be helpful, any point for which I could be helpful, I'll be happy to do that. So with these things, I now close this particular lecture, and you can email me if you need something, some extra. Okay, if you have any time for question, you can ask me the questions, or those who are having the classes, they can leave. So if there is anybody who wants to ask something, you can ask, otherwise you can leave.
So for the consolidation time, fitting the square method and the other method.
Okay.
So can you take one lecture, review it once in a lecture?
Okay, you are in which batch? Batch A or batch
B?
Batch B. Then I'll take the entire class. Maybe you talk to the other students, circulate an email, and those who are interested, then we'll fix up a time, and maybe we we take the class at a convenient time. Even during night, I can take the class. So please talk to your friends, means circulate an email. Those who are interested, then let me see how many people are interested. Accordingly, I'll take the class. If there is only 1 or 2%, I can individually discuss it online. Okay. If there are more number of the students, then I will take a formal kind of the class, lecture type. Okay. And you can have discussion on any topic, and please solve the problems yourself, because what is going to happen, exams will be very late, so by that time you will forget each and everything. So you have good time available, so to solve the problems, and if you have any difficulty, please discuss with us. Okay. Okay.
Thank you, sir.
Okay.